In this lesson and in this unit in particular, we're going to be examining numbers, number systems, number patterns, and things like that. So as an introductory lesson, we just have to go over some ideas we're going to use throughout the number section. So we can break numbers into two categories: real numbers, things you can calculate, things that exist, and complex numbers, things that are more theoretical, for instance, the square root of -1. We're going to concentrate basically on real numbers. Within the real number system, there are 4 different types of subsets, smaller groups of numbers. There are the natural numbers, which are things you can count on your fingers. So 0, 1, 2, 3, 4, all positives, all whole numbers. There's integers. Those include all the natural ones, but also all the negatives. Again, they have to be whole numbers. We sometimes come across z plus or z minus. Z plus would be our positive integers. Z minus would be our negative integers. We have the set q. We call those rational numbers. Rational numbers are anything that can be written as a fraction made up of integers. So for instance, we could have 2/3. That would be a rational number because 2 is an integer and so is 3. The number 5 could be a rational number because really it's 5/1. It turns out anything that's repeating decimals or ending decimals, terminating decimals, can also be written as fractions. And we'll go through some of those examples in just a second. You then have Q naught. That's this little symbol here, Q with an apostrophe beside it. Those are irrational numbers, things that cannot be written as a fraction. For instance, pi. Pi is a never-ending decimal. It doesn't terminate. You can't actually write it as a fraction. Square root of 2, a never-ending, non-repeating decimal. Okay, if we look at the idea of these sets, now the real number system is a series of circles. You have your natural numbers inside, then you have integers, that includes all the natural numbers plus some more, all the rational numbers, which includes all the natural, all the integers, and some more, a separate set, things that aren't rational, and altogether that makes our real number system. And so take a look at some ideas here. I have some numbers. Can you classify them for me by making check marks in which box they fit in? So the number 1.3, is it natural? No, I can't count on my fingers. Is it an integer? No, it's not a whole number. Is it rational? Can I write it as a fraction? And the answer to that would be yes. I can write it as 13/10. So it's a rational number. Pi. Can't count on my fingers. It's not an integer. I can't write it as a fraction. It will not get any check marks. It would really only fit into the R category if we had one down here at the bottom. -6. I can't count on my fingers, but it is an integer. And if it's an integer, I can write it as a fraction. For instance, -6/1. That would be perfect. Sine 60. Can't write that on my fingers. So I can't count on my fingers. It's not an integer. In fact, it's a decimal that never ends. Exact, it's √3/2. Because this is not an integer on top, it doesn't count as a rational number. It exists, but we can't write it as a fraction made up of integers. So no check marks. 6/3. We can write that as 2. Well, I can count on my fingers, so it's natural. It's an integer, and I can write it as a fraction. 6/3. And then we have √2 at the end there. I can't write it count on my fingers. It's not an integer. I can't write it as a fraction. That doesn't fit into any category except for the real numbers. Okay, let's look at some further rational numbers. How do we write these things as fractions? Well, any terminating decimal we can write as a fraction by simply moving our decimal point over. I want to move this over here, so it's 15. And I can do that by putting some zeros on the bottom. 2 spots, 2 zeros. Okay, I end up with 15/100. If I reduce that, divide them both by 5, I can write that as 3/20. And that's true for any terminating decimal. If I have the terminating decimal point 1, 2, 3, I move it over 3 spots, I add 3 zeros, I got a fraction, a rational number. For any terminating decimal, I can write it as a fraction by writing the number that repeats over that many 9s. So 0.222222222 can be written as a fraction of 2 9s. And again, that can happen for any repeating decimal. So if I have 0.45454545, I can write that as 45, two repeating numbers, over 2 nines. If you try to calculate, it turns out that that's what 45 over 99 comes out to, 0.45454545. Some other things we have to deal with numbers. We have to be okay with rounding, scientific notation, and sig figs. IB rules are 3 sig figs for everything unless it says otherwise. So, if an exact value is not necessary, just an estimate, our rule is 5 and higher, round up. So if we look at a simple rounding question here, we have the number 3,624. If I round to the nearest 10, so this is my tens place, I look at the number beside it, it's a 4. I round the keep the tens place the same, so 3,620. The nearest 100, now I'm looking at the 100th spot to figure out my rounding. Look at the previous thing, it's a 2, so I keep it the same. So the nearest 1,000, so I'm thinking about this thing. I look at the next previous spot, it's a 6. That means I have to round up. So we'd round up to 4,000. And you always look to the right to decide if you have to round up or keep it where it is. So I got the number 1.2765. We want to round that to 1 decimal. So 1 decimal is here. To the right of it, I see a 7. I round up to 2 decimals. So I'm looking at the 7. Should I round it up or not? I look at the 6. Got to go up. It's bigger than 5. And to 3 decimals, and I'm looking at the 6. I look to the right of that. I see a 5. 5 or higher, I round up. So 1.277. You often are asked to round things in this next unit we're going to look at. Okay, when you have small numbers or very large numbers, we often use scientific notation to deal with those. Scientific notation is in the form some sort of base times 10 to the power of k. Okay, there are only 2 rules you have to worry about here. Okay. A, your base number, is always between 1 and 10, not including 10. So for instance, 1.23 would be okay, 9.67 would be okay, but you would never see 10.45. And this would be wrong. I'd have to write that as 1.045. My base number is between 1 and 10. And my k value has to be an integer. It's how many spots you're going to move your decimal. So you move your decimal 1 spot, 2 spots, 10 spots, 5 spots. You can't move it half of a spot. It always has to be a whole number. So look at some examples here. 546 million. Let's change it to its opposite form. So I want to take the decimal from here, and I want to move it all the way over to here to make my base number between 1 and 10. Every time I move it to the left, 1, 2, 3, 4, 5, 6, 7, 8 times, that is my exponent. When you move things to the left, you have a big positive exponent. When you move things to the right, it becomes a small negative exponent. Okay, so decimal to the left, positive exponent. Decimal to the right, negative exponent. Now look at the next one. Move my decimal 1, 2, 3 spots. 3.242 times 10 to the negative 3. If I have things in scientific notation, I want to move them back to their standard form. I've got to move my decimal 4 spots. It was a positive, which means it has to move to the right. So 1, 2, 3, 4. Now notice there's an empty gap there, so I got to put a 0 in. So I end up with 64,210. And negative exponent, that means it has to move back to the left. It's got to move left 5 spots. So 1, 2, 3, 4, 5. I fill all those empty spots with zeros. My decimal is right there. So 1, 2, 3, 4, 5, 2. Scientific notation, standard notation. We've got to be kind of comfortable with both. We can do operations. with them also, and we'll get to that in just a second. Last idea, how many digits are we supposed to use? So for IB purposes, unless it says otherwise, we always use 3 sig figs, or exact. If something comes out to exactly 5 million, well then write down 5 million. If it comes out to 5,462,314, you can round that off to 3 sig figs, if you so choose. Okay. Zeros act as placeholders before or after significant figures, and we have to use rounding, like the 5 or higher rule. Okay. Just be careful, don't round until you get to the final answer though. You don't want to prematurely round and change your answers. So let's look at an example, 3 sig figs. This is important, this is important, this is important, this stuff's going to get rounded. So I do my rounding according to the fourth digit. The first 3 are important, the fourth is my rounding. So 7 tells me to round up. So the 3 sig figs, I end up with 2,650,000. The 4 got rounded up according to the fourth figure. But look at B, what's important? This one, this one, this one. This tells me about rounding. It's a 4. So I don't have to round up, I can keep it where it is. So 0.0, 1, 2, 3. The 0 acts as a placeholder here. It doesn't count as important, it's just telling you that there are no tenths. And which helps us in looking at the next one. Okay, placeholder, 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 important, important, important. This talks to me about rounding. So I put my placeholders in, my first 2 sig figs, and my next one has to be rounded up. And then I get 0.33333 repeating. Out of 3 sig figs, I got to keep 3 of them. Okay, so unless it says otherwise, we keep it exact, or 3 sig figs. It's just a general rule. And let's do a little bit of math. I need a calculator for this part. So here's some calculations. Using our calculators, let's evaluate these to 3 sig figs. Okay. We generally show a pre-rounded answer and then our rounded answer. So my calculator types this in, 12.018 divided by 2.334, and I end up with 5.1, 491, and it keeps on going. But what do I really care about? 3 sig figs. So 5 is important, 1's important, and the next digit's important. Do I round up? Well, the 9 tells me yes. So 3 sig figs, 5.15. Try to show your rounding that you've actually taken an answer and then rounded to 3 sig figs. Okay, in my calculator, I punch all this in. I'm going to put brackets around so I can do it all at one time. And I end up with 7.6426, which to 3 sig figs, 7.64. A premature answer, and then my final answer. I got a scientific notation question. So I can enter in my calculator if I know how, this in scientific notation, or I can change this to standard form. Okay, 2.65 to the 10 to the 4, I move my decimal 4 spots, I add 2 zeros in. 4.1 times 10 to the 7, 1 spot, 2, 3, 4, 5, 6, 7 spots. Put into my calculator. I end up with 1.0865 times 10 to the power of 12. My calculator went to scientific notation automatically. Now that's more than 3 sig figs. There's a whole bunch of stuff. What's important? The 1, the 0, not a placeholder because between significant figures, and the next digit. Because I have a 6 here, I have to round up to a 9. The 10 to the 12, those are placeholders. Those are a whole bunch of zeros at the end of this question. And last one, last set of examples here. So a field is 91.4 meters long, 68.5 meters wide. Calculate its area. Well, we know the area of a rectangle. Length times width. So in our calculators, we need to do this. But notice, we're given meters and it asks us in centimeters. So I need to make a little conversion first. Meters to centimeters. 91.4 meters is times it by 100. 91,400 centimeters. 68.5. 68,500 centimeters. Okay, meters to centimeters we're going to multiply by 100. It's easier to do conversions first and then multiplication. So I end up with 91,400 times 68,500, and that would give me 62,609,000 centimeters to 3 sig figs. Okay. Part B asks us to put that in scientific notation. Well, we can do that. My first number has got to be between 1 and 10, so 6 point. I fill all the rest of the decimals in, 2609, so all the other significant numbers, times 10 to the, our decimal used to be here, we got to move it over 1, 2, 3, 4, 5, 6, 7 spots. There's your scientific notation answer. Yeah, our last idea is sometimes we have error. When we round things in particular, it's taken an answer we used to have and changed it slightly. So a formula we have for error, or we call this percentage error, is you take your exact value and your approximate value and you figure out the difference between them. If you then divide that by the exact value, you've created a percentage, a total out of something. Okay? New symbol for us, these little lines here, we've learned about these. These are absolute signs. So all that's doing is taking our value and making it a positive. Error is always referred to in a positive way, how much error you have. So for example, if we look back to the field for a second, and we found out the answer was 62,609,000 centimeters. Well, what if we had rounded that to 3 sig figs? 62.6. How much error has that introduced? So our error, oops, that is not good spelling. Our error will be the absolute of our approximate value, that's our rounded answer, 62,600,000, minus the actual answer, we know it's 62,609,000, divided by what the actual answer was, 62.6, and then we're going to turn that into a percent afterwards, and just so it's easier to discuss. So if we subtract on top, and then divide by the bottom, times it by 100%, we end up with 0.0144 to 3 sig figs percent. Again, everything's about 3 sig figs or exact, unless it says otherwise. So it's not a huge error, like less than 1% error, right? Less than 1/10 of a percent error, in fact. Okay? But there is an error when you round things, and that's always true. That's a formula you should know. I put on your learning goal sheet just so you have it. The biggest mistake people make with that one is what thing to put on the bottom. Make sure it's your exact answer that goes on the bottom. Okay, today's homework is a handout. Okay, print it off the website if you need to. And that's just an introduction to how we can use numbers and way we're going to work with numbers.